Hey folks, welcome back. This is the next lecture in my performance-based liquefaction hazard analysis series. And as I mentioned in the earlier videos, I'm walking through many of the preliminary background topics to understand the need, why we need to have a performance-based approach, and what goes into a performance-based liquefaction hazard assessment approach. So the next thing that we need to understand is how we take ground motion prediction equations and use them for the purpose of predicting some future earthquake that hasn't occurred yet. And the process of doing that, of using those equations to predict strong ground motions for some future earthquake, is what we call a seismic hazard analysis, or an SHA. Sometimes you'll see it look like that, an SHA. The seismic hazard analysis really comes in two flavors. There is a deterministic seismic hazard analysis, DSHA, and there is also a probabilistic seismic hazard analysis, or a PSHA. Now, there's also a different type of PSHA that's coming online. It's called a physics-based seismic hazard analysis. And I'm not going to talk about that in this or my other lecture that I've taken these slides from in my 545 class. It suffices to say that seismologists and engineers and earth scientists are getting good enough at understanding the fundamental physics of what's going on in plate tectonics and in the way that waves attenuate and travel through the earth, that they're able to, using very powerful computers, simulate an earthquake all the way from the rupture of the fault to the propagation of the waves to the waves arriving at the ground surface, and then the types of effects that are occurring at the ground surface. Now that's very advanced stuff, this physics-based. So we're not going to talk about that, and very few engineering practitioners actually use those. Instead, we're going to talk about these two right here, the DSHA and the PSHA. So let's jump in first to a deterministic seismic hazard analysis, the DSHA. This is what I affectionately like to call the original seismic hazard analysis. It was the first seismic hazard analysis, and it really makes sense. I mean, it's also the common sense seismic hazard analysis. So in other words, if you're the engineer and you have three seismic sources, it's easier if I just show. So again, here's your site. It's my stereotypical house on soil, and you have three seismic sources located all around you. And I were to just say, hey, do a common sense approach to predict which ground motion you should design for your site right here. Well, a common sense approach that most engineers could come up with on their own was they say, well, first I'll analyze this seismic source and predict the waves from it, and then I'll analyze this seismic source and I'll predict the ground motions from that. Then I'll analyze that seismic source and I'll predict the ground motions from that. Then I'll compare those three ground motions, and whichever one is the biggest, maybe it's this one right here, that's the one I'll design to. And if I design to that one because it's the biggest, then I'll be okay if that one or that one were to occur. And folks, that's basically the DSHA in a nutshell. It really represents a scenario analysis, so you're analyzing each seismic source one at a time, and it's intended to be conservative, meaning you're going to pick the larger of all the scenarios that you analyze for your design. So here are the steps. The first step is you need to identify all of your active sources that could contribute. Now bear in mind I have this in parentheses because it's such a subjective word. What do I mean by active? There's faults all around us, everywhere you go in this country. And people may wonder, well, if there's faults, that means there's earthquakes. Well, not necessarily. Many faults haven't ruptured in millions and millions of years. So what's the likelihood that fault's going to rupture during the lifetime of your structure that you're designing? So the idea of identifying the active sources is to find the faults that we believe actually have a legitimate chance at rupturing sometime in the next several thousands of years. Usually the way that we judge that, by the way, is going back and determining which faults have ruptured in the last, say, 10,000 or 100,000. Even conservatively, we might even say which fault has ruptured in the last million years or so. And in the age of the Earth, a million years ago is a blink of an eye. It's really nothing. So these are essentially young faults. Now, once we find those active sources, we have to assign a maximum credible magnitude to each of those sources. And we have ways to do that. I won't delve into them here in this crash course, but if you want to learn more, you can go back and look at this topic in my 545 class. Now the next step is we have to determine the distance from each of those sources to our site. Then we're going to use attenuation relationships, and remember, instead of attenuation relationships, I started to encourage you to use the term ground motion prediction equations, or GMPEs, instead. We're trying to move away from the use of attenuation relationships. So use your GMPEs to compute the ground motions for every one of those sources, and then identify the governing source, so the one that is typically the largest ground motion, and that's the one you're going to design to. That is the DSHA. Now there's two major problems or shortcomings with the DSHA. The first is that nowhere in that process that we just walked through did you deal at all with the likelihood or any of the uncertainties associated with the problem. You're just assuming that fault will have an earthquake during the lifetime of your structure, and that's an assumption you're making for your analysis with no type of thinking of well, could the magnitude be higher? Could the magnitude be lower? What if the fault ruptures at a different part of the fault instead of the closest segment to my site? All of those things, it doesn't deal with uncertainty. And related to that, it doesn't deal with the likelihood of the earthquake. It only deals with the possibility of the earthquake. And if it's possible, in a DSHA, it happened. It doesn't matter if it's unlikely or not. If it's possible, you assume it happened. So a little thought experiment I like to go through with my students is consider if you're doing a DSHA for a building in San Francisco and the same building in Memphis, Tennessee. And now both these locations have experienced a magnitude 8.0 earthquake or so. New Madrid zone near Memphis has had 8.0 earthquakes in the past, and San Francisco, they've got numerous faults around them that could generate a magnitude 8.0, most famously the San Andreas fault. So with this type of approach then, if both locations are equally capable of experiencing a magnitude 8.0, then with this type of approach you would design buildings in both locations to have the same seismic resistance. Now, if that doesn't sit right to you, and you say, wait, that doesn't sound right at all, the building in San Francisco should be designed much more resiliently for earthquakes than the one in Memphis. And I would ask why. Why is that the case? Well, because the reason for that is because the likelihood of the magnitude 8.0 earthquake in San Francisco is much, much higher in the lifetime of your building than the likelihood of it occurring in Memphis, Tennessee. And so a DSHA doesn't capture any of these effects. And that leads me to the PSHA, the Probabilistic Seismic Hazard Analysis. It was really developed in the late 1960s and in the 1970s, and it was developed as a means for trying to account for and quantify all of the uncertainties involved in a seismic hazard analysis. And if you sit down and really think about it, there's a lot of uncertainties. In fact, imagine you're sitting across the table from me, and I'm looking at you, and you're looking at me, and I say, hey, you, tell me when the next earthquake's going to be. And you're going to go, I have no idea. And I'm going to say, well, tell me where it's going to be. And you're going to say, I don't know. Well, how big will it be? I have no clue. Why are you asking me these weird questions? And these are all of the uncertainties that go into a seismic hazard analysis. We don't know where the earthquake will be. We don't know how big the earthquake will be. Even if we knew where and how big the earthquake would be, we still have a lot of uncertainty of how large the ground motions at our site are going to be. And then we don't know when the earthquake's going to occur. So, I mean, when you look at this list, it's like, well, what do we know? We know where the potential seismic sources are. We know the historic pattern of how often these seismic sources have gone in their past. And we have evidence to inform us of how large past earthquakes have been. And so if we project those out to the future, we can have a pretty good idea of the likelihoods of future events and the size of those events. But we don't know on which one of those sources each of those events or the next event could occur. So that's the whole point of a PSHA is again, here's your site, and you have all these different faults and seismic sources around your site, just like we did with the DSHA. But now in this instance, instead of just analyzing each one like it's going to go, we're going to look at the recurrence or the likelihood of different magnitudes occurring on each one of these faults. And then we're going to cycle through every possible magnitude occurring on every possible fault. And from every possible magnitude and every possible fault, we're going to get every possible ground motion that our site might experience from each of those scenario events. And then if we aggregate all of these scenarios together with their corresponding likelihoods, we're going to develop an estimate of the probability of exceeding various ground motion levels using what's called a seismic hazard curve. So I've had individuals ask me in the past, and they say, well, so what's the difference between a deterministic seismic hazard analysis and a probabilistic seismic hazard analysis? And the main difference is that a probabilistic seismic hazard analysis is a big collection of millions of deterministic seismic hazard analyses, each weighted by their corresponding likelihood and aggregated together. A deterministic seismic hazard analysis is a conservative but simple estimate of the attempt to estimate the worst credible scenario that might occur and affect your site. That's the main difference between these two. Okay. Oops, I didn't realize I wrote over my little pop-up there. Now, by the way, all these little pop-ups that are here, like with the recurrence laws, Gutenberg, Richter law, characteristic earthquake law, these are all discussed in depth in my 545 lecture, and you're welcome to go over and listen to those recordings. You'll learn something great about those recurrence laws. And we've already discussed attenuation relationships, or GMPEs, quite a bit, so we don't need to worry too much about those. But in this crash course, I am not going to go into detail on like recurrence laws or seismic hazard curves. So this is what a PSHA looks like in equation form, right? So this is the PSHA. And it looks like a mathematician's nightmare, or maybe their Christmas morning dream come true, depending on how much they like integrals. But really what we've got here are a bunch of summations that deal with all the different aspects and the different uncertainties. So let's walk through all these different uncertainties. So first of all, with these this term here of n sub s, that s refers to the different sources or sites. So we're going to iterate through all of the sources that are surrounding our site, along with their various recurrence rates. That's what that Greek symbol nu stands for. We are also going to account for all of the possible source to site distances. That's what this R stands for. That's source to site distance. So we're going to iterate through all the possible locations on those seismic sources where earthquakes or the fault might rupture, and then we're going to compute the corresponding distance from that rupture to our site and account for the probabilities then of those different distances from our site. We're going to account for all the different magnitudes corresponding to each seismic source. That's what the different M's stand for. So we're going to iterate through every possible magnitude. And this little term right here, the probability of ground motion y exceeding some value y star, that is considering the probability and the uncertainty in our ground motion prediction equations, because there's certainly scatter in those things as well. And so if we just step back and look at the beauty that lays before you here, what you have in this mathematical smorgasbord of a dessert here is we are iterating through every single seismic source. For each of those sources, we're iterating through every possible magnitude that that source might experience. And for every one of those magnitudes, we're iterating through every possible location that that fault rupture might occur upon. And for every one of those magnitudes and location combinations, we're estimating every possible ground motion value that might occur from that earthquake. And we're summing all of this, aggregating it all together to get one number. Pretty incredible when you think about it. And what is that number? What is that lambda value that we were looking at? It is the mean annual rate of exceedance. And so it's a way to quantify the likelihood of different ground motion values occurring at our site. And so a seismic hazard curve relates likelihood to various ground motion values. Now we can break them out by individual sources, like source 1, source 2, source 3, or we can aggregate them together and just do a total seismic hazard curve that considers all sources combined. And that's generally what we use when we use probabilistic ground motions. So understand, when I talk about probabilistic ground motions, this is what I'm talking about, seismic hazard curves. Seismic hazard curves develop from PSHAs. That's what I'm talking about. So in a PSHA, these hazard curves are computed, everything comes together to give us the total seismic hazard, and One thing that you might find interesting, if this terminology of the mean annual rate of exceedance seems vague to you or nebulous, you don't really understand what it means, a lot of you are more comfortable with this term, the return period. The return period is the average amount of time that passes between experiences of a given intensity. So, in other words, if I want to know the return period of having a flood that achieves a certain level in this river near me, then I could say, okay, well, the time that typically passes on average between events that large, that is the return period of that level of flood. So if we want to get the return period, all it is the reciprocal of lambda. It's the reciprocal of the mean annual rate of exceedance. So that tells you the relationship between those two. And how do we use seismic hazard curves? So do you remember the fourth source of uncertainty we talked about with predicting future earthquakes? Yeah, it's the uncertainty dealing with time. When will that earthquake occur? We really don't know. That uncertainty is what we call the temporal uncertainty. And temporal uncertainty is handled not with things like time machines or divination or anything like that, but it's handled with statistics and probability theory. So in order to predict the likelihood of a future earthquake occurring at some given time interval in the future, we're going to use something called that treats all of these events as random and independent from one another, and we're going to then apply what's called the Poisson probability model. So the Poisson probability model is the same probability model of rolling dice. In other words, if I want to know the probability of rolling a 7 with 2 die, I can compute that probability pretty simply. Now, if I want to know the probability of rolling a 7 on my next throw, it has nothing to do with what I rolled on the previous throw. Every single throw is independent of one another. Unless, of course, I want to know the probability of throwing a 7 on this roll and the next roll, one right after the other, then it becomes dependent. But in every single throw is an independent event, and that's a fundamental assumption with the Poisson probability model. In other words, every single earthquake is considered an independent event and unrelated to the previous earthquake that happened on that fault, and unrelated to the earthquake that will happen after the next one that you're talking about. So if we treat earthquakes like random and independent processes, then we can use this Poisson probability model, and that's given with this equation right here. So that term from our PSHA, that probability of exceeding some given ground motion y star, we can compute that with this equation right here. And this equation is a function of the seismic hazard curve value that corresponds to the ground motion value y star that you're interested in, and then the time frame that you're interested in the same unit of time as your hazard curve, typically years. So this then would be like the design life of your structure or your levee or whatever it is you're interested in. And that's how we can get probabilities from these different seismic hazard curves. The last thing I want to talk about with probabilistic ground motions is, do you remember how I said it's taking millions and millions of deterministic seismic hazard analyses and it's assigning weights or likelihoods to them, and then it's aggregating them together, adding them all up to come up with one number, that lambda y. Right? That all of that aggregation produces one number. But lots of times we want to know which deterministic scenario events contributed the most to that one number. So it's useful lots of times for us to deaggregate or disaggregate, another way of saying it, that data back down to the individual scenario events so that we can look at them and see. And these types of plots are what we call deaggregations or disaggregation plots. So typically they look like this. We have the percent contribution to our lambda value. We have the source to site distance for the different events, and we have the magnitudes from the different events. And so we start to see the breakout. So in this particular example, we see the events that seem to be governing our probabilistic seismic hazard are given right here, which they seem to correspond to, about a magnitude 6.7, 6.8, maybe 7.0 earthquake, and at a very short distance, less than 10 kilometers from our site. So those would be the scenario events that are most contributing to this probabilistic hazard. So from these disaggregation or deaggregation plots, we can get things like the mean magnitude and distance of all of our possible sources. And we can get also what's called the mode or the modal magnitude and distance. And that always corresponds to whichever magnitude and distance combination gives you the highest bin that contributes, that one scenario contributes the most hazard to the combined hazard. That's the mode. Okay, that's basically the end of the crash course in ground motion seismic hazard analysis, guys. So again, if we moved very fast, that's because we did. And if you feel like you've been drinking from a fire hose, that's because you have. I take about 2 weeks in my graduate class to walk my students through what I just walked you through in less than 40 minutes probably. So feel free, if you want to learn more about this topic, to go find my lectures on this topic in my 545 class. You can feel free to watch those videos. They're great. But what I wanted to convey to you for the purpose of performance-based liquefaction is that in order to account for all the uncertainties related to liquefaction, we have to account for the uncertainties related to future ground motions. And the way we do that, PSHA. That's the moral of the story. Next time, in the next lecture, we're going to dive into the fundamentals and the basics that deal with soil liquefaction. We're going to look at the mechanics. We're going to look at what the phenomenon is and how we've come to be able to predict its occurrence in various soils. So feel free to click on that video, and I'll catch you the next time. Thank you, guys.